Thank you, and good afternoon, and welcome back to the Colloquium. It's my job to give the last lecture. And we're going to end up with an open session if we have an audience. It looks like we may be finishing a little earlier than we expected. I'm presenting this on behalf of the LibreSpace team, and it's specifically about SatNOGS, satellite with no ground station. I'll explain what I mean by that in a second. It's from the LibreSpace Foundation, who were set up to basically to do a lot of things with open source, as Michelle was talking about earlier on today. They're a non-for-profit organisation, and they're founded in 2015, so about 10 years old. I got involved with them in the early days. We did a lot of work with ESA. We got involved with the Genso project as well in the early days for basically a distributed ground system. They say it's 100% space technology. That's the only thing they're interested in. It's either ground stations or building satellites or building software to enable the development of systems. It's 100% open source in the same way that Michelle said with their systems. And it's a little bit about the SatNOGS project itself. As I said, it's been going about 10 years. It's a very small team, but the worldwide population actually involved in SatNOGS is quite considerable. I did a lot of work with the FunCube and the FunCube Data Warehouse, and we've been a parallel sort of pair of projects, watching each other's activities over the years. It's a network of ground stations. One of the first things they did was actually to design their own ground station. So basically, it was an off the shelf, so open source, using commercial components. Basically, a lot of the very, very early days of 3D printing, and they put together their own ground station. That hasn't really taken off. It's been more a case of the software that will actually be distributed for people to use with their own ground stations. They have an open source stack. It's a set of software projects. As I've said, it's a small amount of hardware projects these days, and it's the services that provide the connection between the people's ground stations and the data warehouse, which is similar to the one that FunCube has. The idea was, in the same way that Genso, the Global Educational Network for Satellite Operations, which is what Genso stands for, it was to bring together things like universities, organizations, space agencies, to allow organizations to use the ground stations to watch each other's satellites. The problem is, because of the orbital dynamics, you only ever see your own. If you're a university and you put a CubeSat up, you'd only see it something like 12 times a day. From 2 degrees up to overhead. And basically, you probably only get, of those 12 orbits, you probably only get 6 worthwhile ones. So, and the rest of the time, your ground station remained redundant. So what a good idea if you could actually share that resource with other organizations. The LibreSpace, the Genso project, and the FunCube all use that same model. The system is intended for amateur radio, of course. I'll talk a little bit more about commercial side of it in a second. It's UHF and VHF, L-band, S-band, but it all depends what the ground station provider has. I'll show you what we have at Goonhilly at the end of the presentation, and I've actually set it up to do a bit of capture in the next half an hour or so while I'm speaking. But I think I've set up the system to take about four passes of various satellites. Lots of things in low Earth orbit, as we've seen from the talks this morning. Overhead at any one time, there's probably something like 10 LEO satellites we can pick up with the Libra on UHF. It's not just the amount, it's not just capture. The early days of the Libra system was basically, can we see a signal? That was the basic thing. It's been extended such that the data coming down from the satellite through the ground station into the data warehouse can then be processed, be it SSTV, be it telemetry, or whatever. And because it's open source, the satellite developers can use the Libra system to put a back end on to actually capture the data. It was also intended for STEM outreach, so people can learn about satellite fundamentals. It's nice doing your modelling, but it's also nice to see your own satellite data coming down. The interesting thing that's come out of it in latter days is a launch will carry something like, well, the maximum number of CubeSats ever launched at the same time was 105 about 20 odd years ago. But launches now are becoming more and more common, and the number of vehicles being launched at the same time is in 10s and 20s if it's a multiple pod launch. You have the model of what the rocket's going to do in terms of its Keplerian elements. Some flights are using what's called a free flyer. So once the rocket's gone up, primary payload's gone off, you then launch another vehicle which basically just contains CubeSats or microsats. And they're timed to go off at various points. So you have the basic elements, but you then can't actually work out in this cluster of small satellites which one's which. The Libra system, well, I'll show you an image in a few seconds. We should probably demonstrate with what we can do at Goonhilly. Is you've got you end up with a waterfall of the telemetry of the bandwidth, and in the bandwidth you can actually see Doppler curves, as well as what would be a piece of telemetry you're expecting. In the early days of a launch, you may see multiple Doppler curves, and they can use the Libra system just for the timing of, when would you expect to see the Doppler actually be in the center of that frequency, and they can work out from the timing. They can actually reverse engineer what the Keplerian elements are, and that's been a nice side effect they've come across in the development. They've done a lot of work with the element definition. They take all the information from Celestrak, and it's updated every day. I'll talk about the specifics about a ground station in a second. They provide basically a Raspberry Pi image that you can install literally put onto your SD card, or they will provide the source code as well, which they can compile up, etc. That piece of software basically talks back to a data warehouse, or they call it in their case they call it the network. I'll demonstrate how that gets used when I get onto the Goonhilly system. But basically, you say, here's my ground station. What are the future passes? And it'll give you the future passes for the next 24 hours. And you select, I want to track that satellite, that satellite, that satellite. But it's the nature of it is you're trying to get the whole of a satellite pass. Because they can possibly have in an hour they can have something like 40 satellites going overhead. So you could, but you end up with an awful lot of overlap between them. So the system's quite capable of saying, I've selected that satellite, what are the next set? And it'll actually work out what that overlap is. Well, you can't have that one. Here's the next one for you. You can determine if you're a satellite builder, you can make the system choose your satellite from the list. Or if you are a research organization and you know there's a cluster of satellites that you want to use, you just tick them off. But the interesting thing is that not only you can use your ground station, other people can use it and schedule passes on your ground station. So, which is quite interesting. The Goonhilly one occasionally sort of pops up and says, "Oh, so I've got about 5 people listening for this satellite. I haven't scheduled that." So it's very much a collaborative thing. There are 280. These slides are probably about 12 months old, I think. So, and the number of ground stations at that point was 287, 163 in testing. There is a difference between the two. The live stations can upload their data to the warehouse and get it processed. Testing ones are basically just operating locally on the Raspberry Pi. As I said, they have a set of ground stations, 287, and the SatNOGS network, which I mentioned. We can schedule. It hasn't come up on that screen, unfortunately. There we go. We can schedule individual passes. We can say, given a time span, then in the next 3 hours, what satellites are coming up overhead, and we get a graph basically of all the satellites that are available. You can go click, 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 and choose the ones you want. This is what I was saying about you don't necessarily have to choose your own satellite. You can choose other people's. And if you go silly, you can say, in the next n hours, look at those next 25 satellites I've chosen. What are the availabilities? And the width of the little bars basically indicates how long the overhead pass is going to be. And next slide. Once you've had a pass, it's not very obvious, but I'll point out the information on the screen. Once a pass has happened, the network will store the information that's been uploaded from the ground station. You end up with the waterfall being recorded. If there's any audio available, that's recorded as well. If there's a specific telemetry decoder been written for that satellite, that's available as well. And that's what the little image, you probably can't see them clearly here, but there are a set of images to give you an indication of what the network thinks it's found. It's then down to the individual operator to actually vet those received signals. Let's go on to the next slide. And you can see in the middle the waterfall. I'm hoping you can just about make it out. There's actually a piece of telemetry in amongst that. It's a bit too small for me to see which satellite it was. But on the right-hand side it's actually captured telemetry frames. And if you're the user of that satellite, you can then download them, put them into your processing package, and get the telemetry off. It's also got a database of satellites. So basically, it's got the basic characteristics of what the satellite looks like. its operational characteristics. So it's a nice repository for information. We can also get a bit more information about what the type of the satellite is, and what the updated information from Celestrak is. So you always know you're getting up-to-date information. I like pictures. I'm trying to find some more pictures. There we go. We've mentioned that we can do satellite identification through the Dopplers. We've got the decoders available. We've got the dashboards available. So basically, this is the overall picture of what the SatNOGS system is. It's the system that, as it was when it started out, was about 400 ground stations. 10,000 observations per day and demodulated data. In the same way that FunCube has, so the FunCube data warehouse has gone down and up in terms of the number of ground stations available. They have the same thing as well. People become interested, people lose interest. You get a new surge of people coming on board because a particular satellite's been launched, and that's been given more publicity. So the number of people using the system comes and goes. The database has tracked 2,000, probably about 2,400 satellites by now, and over 4,300 different transmitters, be they on VHF, UHF, S-band, L-band, and 2.85 million demodulated frames. So basically where they've actually got something in the waterfall and the demodulators have worked. FunCube is a similar sort of number as well. They've got about, as I've said, the number of decoders they've got is in the region of 100. And they've got lots and lots of them. They keep the TLE sets for the current TLEs, and they also keep historical ones as well. Using that mechanism I said about the Doppler shift, they've actually managed to identify at least 220 new satellites in orbit. And how to contribute? If you have a Raspberry Pi and you have an RTL dongle, an omnidirectional antenna, you can get onto the SatNOGS network, which is exactly what we have at Goonhilly. Give me a second. And this is what we have at the Goonhilly station. Oops. Why am I not getting any video? Oh, it's on the right. There we had the same problem. Oh, there we go. Here he comes, yes. Bear with me a second. You should about see it. This is on one of the huts at Goonhilly. The small turnstile is actually our SatNOGS antenna. You can imagine we've got some much larger antennas at Goonhilly. The one behind it is actually the VHF web SDR that's actually that's on the web at it's available to everybody. The SatNOGS system is available. Trouble is, I can't drive. I can't drive it if it's on. I'd have to look at the screen at the same time, unfortunately. But going back to what I said, we can schedule passes. We can then vet what the system has recovered. It's either a waterfall, as I said, or it's a piece of audio, or we've written a decoder ourselves. Some of the SSTV satellites, it will actually decode the ISS. It will actually record the ISS's audio on the VHF, UHF linear FM transponder, and if it's transmitting SSB, it'll actually SSTV. It will decode the SSTV image and actually record it for viewing. It's an interesting little project. I'm running one at home. I probably track about 4 or 5 satellites a day, but as I said, most people just do it for interest. We try and keep this. I try and keep this one fairly active, but it's simply, if you have Raspberry Pi that's going spare, you have an SD card that's going spare. A simple dipole on 2 meters will work equally well. If you've got a turnstile with a preamp, as always, it gets better. The system can drive a rotator using the Hamlib package to call out the G5500. But that's then the commitment of that rotator and antenna has been assigned to the SatNOGS system. It's fun. It's great fun, and it's worthwhile. And that's a quick overview of SatNOGS. Thank you very much.